Okay, good afternoon, everybody. My name is Rudy Shankar. I am the director of the Energy Systems Energy Program at Lehigh University, and welcome to the fifth seminar of, of the ESEC Spring Series. And this presentation is titled Practical Realities of the Energy Transition. And all of last semester and so far this semester, we've been looking at energy transition, especially this semester, we've been focusing on what are some of practical issues. And this presentation it would be ideal for what we've heard for the last 1.5 semesters. And to make this presentation is Stan Rosinski, a technical executive with EPRI and a longtime colleague of mine. And so I'm really glad to welcome Stan. Before he starts talking, I will introduce Stan. He's a technical executive with Electric Power Research Institute, and he brings nearly 40 years of experience. And I'm still kind of startled that he's been around for 40 years. He's a lot younger than that, but anyway, he's been there for 40 years. In power generation to identify risks and mitigation strategies and provide site level and fleet level analysis and pathways to support the energy transition to a decarbonized future. STAN also supports activities focused on improving reliability and addressing age-related degradation issues in major fossil power generation components. He previously led the EPRI's renewable generation research to increase deployment and improve potential on improve performance and enhance reliability. He served on the National Academy's Committee on Energy Resource Potential in DOE lands. Additionally, Stan led EPRI's Technology Innovation Program, directing fundamental research and development process across the Institute to accelerate application of advanced science and technology. And he also led the reactor pressure vessel integrity and fatigue issue task groups under the Nuclear Material Reliability Program. Prior to EPRI, Stan was a senior member of technical staff at Sandia. He was responsible for the resolution of light water reactor material related issues and served as chief metallurgical consultant for the U.S. Department of Energy. He received a professional engineer degree, from honorary degree from the University of Missouri at Rolla. He's a co-author of 3 books, author, co-author, or project manager of over 240 publications. That's remarkable, Stan. So welcome, Stan, and the floor is yours.
All right. Thank you, Ramesh. And it's a pleasure to be here this afternoon. I hope everybody can hear me okay. If you have any audio issues, please send a note to Ramesh in the chat, and he can let me know. I will have to say, Ramesh, that you and I have been colleagues for decades now, but I don't know what you're doing because you haven't aged a bit since I last saw you at EPRI. So keep up the good work.
Well, that's the AI working.
Yeah, so my topic today is I'm going to talk about the energy transition. It's obviously a very relevant topic. It's a very discussed topic in the industry. But I'm approaching it from a little bit different perspective, and I'll get to this later in the talk, but I manage a program that is looking at what we like to call the practical realities of the energy transition. What are some of the challenges that we see the industry is likely going to face in trying to decarbonize the energy economy? I'm first going to give a few minute introduction to EPRI. I'm not sure if everyone on the phone is familiar with EPRI, so I'll give a few introductory remarks here. And then I'll get into the energy transition itself. I'm going to talk a little bit about some of the global trends that we're seeing, but I'm only going to do this at more of an overview level. Next Monday at this time, you are in for a treat as Michael Caravaggio, one of our vice presidents at EPRI, is going to talk about more of a deep dive into some of the global trends and the global state of technology in terms of the energy transition. But I'll give you a little bit of an overview of that today. I'll also talk about some of the technology aspects, both the current technologies and new technologies that we believe will have a critical role in the energy transition. Talk a little bit about the industry as a whole, and how those will have a role to play in the energy economy. And then I'll get into, throughout actually the presentation, the real crux of the topic. What are some of the practical realities? What are some of the realistic challenges that we think the industry is going to face, and what EPRI is doing to try and address those. And then I'll have a few closing comments. Now I've got about an hour of presentation. What I'll try and do, in case there are questions that come up during the presentation, I don't necessarily want to hold all of them until the end, so I'll try and stop a couple times during the presentation to see if there's any questions. And then, of course, we should have time at the end. All right, very brief introduction to EPRI. EPRI has been around since the early 1970s. We actually were formed following a blackout in the northeast of the US in the late 60s. And the idea at the time was that the energy industry needed to be able to do the appropriate research and development to essentially keep such blackouts from happening again. That really forms a core of what EPRI is all about. As you can see on the screen, our mission is to advance safe, reliable, and affordable clean energy. And you're going to hear that theme throughout the presentation, because a variety of technologies, energy technologies, can be implemented, but the challenge is they must be safe, they must be reliable. And I'll show you some instances where reliability has been challenged recently, and they must remain affordable. If we get into a situation where energy becomes a choice, which it already is with some people, between food and energy, right, we have to make sure that we keep energy as affordable as possible. EPRI is a collaborative organization. We are also a nonprofit, which puts us in a rather unique business model, so that we can engage with our customers and the general public as well. EPRI's global presence, we are in approximately 40 countries, and more than 400 energy companies are engaged in collaboration activities with EPRI. We are on 6 of the 7 continents. Our funding is approximately $500 million per year, and the vast majority of that goes back into collaborative R&D. So there's a significant leverage in each of our members' ability that they can tap into when we look at some of our research efforts. In fact, some of the research programs at EPRI, well over 50% of the funding in a specific area may be from international sources. EPRI's role is rather unique. We view ourselves, and I think credit to EPRI's business model, society views us as a trusted source of information. We are independent. Our funding will come from a variety of sources, whether it's Department of Energy or state research organizations. It could be from the utility industry. It could be from other groups as well. But we are an independent source of information, so we will engage with industry, lawmakers, policymakers, thought leaders, the regulatory community, and of course, we try to enhance value to members and society at large. One of our roles is really to accelerate technology advancements. And I think this is an area where EPRI is in a unique role. We will engage with laboratories and universities, looking at the basic research concepts. We also look at existing technologies from other industries to see how perhaps we can apply that through targeted research for the benefit of our members. We can bridge that gap between laboratories and universities, different suppliers and vendors, and bring that into a collaborative model we can then use for the benefit of our members. One of the other aspects that EPRI is engaged in is trying to understand where the industry may be heading in the future. As you might imagine, most of the energy industry is looking at more of a near-term or short-term focus in terms of generating power, generating energy. EPRI's role is really to try and provide that thought leadership, working with our stakeholders to try and determine and understand the risks associated with what could be happening in the future. I just have a couple examples here on the screen. We're looking at near-term activities, such as what might be happening in the 10 to 15-year time period. Decarbonization, of course, is certainly in the forefront of a lot of discussions. Resiliency of the climate or of the energy grid, energy system is also a critical aspect. But as we start looking into longer term time periods, such as 15 to 30 years, we really believe there will be a transformation of the energy systems. We're going to be focused more on net zero clean energy production, but we also make sure that that future energy system is resilient and utilizes smart integration of energy carriers. And again, we want to make sure that our energy system is affordable, reliable, and clean. Okay, with that, let me start the overview here and get into a little bit of some of the global trends that we're seeing. Now let's hope this video comes out. Yeah, here we go. I wanted to show this because we have been in a transition, an energy transition for decades, right? And as you can see from the chart, started in 1949 through roughly today, we've seen a change in how the energy resource mix, the different energy technologies that are dominant. Certainly coal has been king for decades, but as you see, it quickly becomes overtaken by natural gas. Nuclear is still a relevant contributor to the energy supply in the US, but now we also see solar and wind as being more significant contributors, whereas decades ago, they were not even really part of the equation. So what makes today's energy transition really that different, since obviously this has been happening for quite some time? I think the way I would like to put it is that this decade is really represents what we call a perfect storm of both challenges and opportunities. What do we mean by that? Well, we're seeing demand growth accelerating significantly. I'll talk about that in a minute. We've seen more severe weather events that are continuing, and in some places, getting even more severe than previously. Many countries have aggressive carbon goals in place. I'll talk about some of that in the US as well. Granted, there is some uncertainty as to, as there would be with any administration, as to what may continue, but at least I want to set the landscape of what the situation looks like today. We also have a situation where we believe that there are new technologies that can get us to a decarbonized net zero energy supply that are needed, but they're not quite ready. They're still in development stage. Some of them may be in demonstration stage, but they still have a ways to go. But we need to accelerate that. And of course, at the end of the day, affordability and reliability is critical. There is a document that I would like to make you aware of. You can either scan the QR code on the screen. I also show a number here at the bottom of the screen. If you go to EPRI.com, you might need to sign up for a user ID, but this is a publicly available document that we put out at the end of 2023. It's only about 10 pages or so, but what it does is it provides a high-level overview, some of which I'm talking about in this presentation, of what is practical potential of today's energy supply resources. It discusses a bit of the challenges that we think these energy resources may face in moving forward, and the importance of resilience of those technologies. But again, this is a publicly available paper, and I think it would be a good reference if you choose to download it. All of this energy supply is also going to be driven by in some respect, of what are the existing carbon regulations. And as I show on this graph here, it varies all over the world. There are many countries that have no existing carbon regulations at this time. There are countries that have perhaps either a carbon tax that has been implemented, or emissions trading scheme has been implemented, or both. And certainly as you look at country by country, this is going to have an impact on those technologies that may be considered relevant for the energy transition in those countries. But we need to step back a minute and look at this more of a global scale. What I'm going to show here is for those G20 countries, their electricity supply. Now, if you look at the amount of electricity that's been generated over the last 24, 25 years or so, as you might expect, as you see demand increase with more industrialization and different industries, you start to see a demand in the general increase in electricity. A couple things are interesting in this graph, though. Nuclear has remained fairly stable over the last 20 years. All those countries in the G20 group that have nuclear are maintaining those technologies. License renewal that Ramesh and I were both involved in the early days has been effective in keeping the existing plants operating. We will get into a bit later on some of the newer technologies that we foresee as well. So nuclear has remained fairly stable. It used to be a much larger percentage of the electricity mix, and now it's only about 10%, even though the amount of electricity produced has remained relatively constant. You'll see a couple other interesting aspects as well. Solar and wind, which are the top yellow and green bars, has increased dramatically. And that's a very common theme across many of these countries. You see a very significant increase in the amount of renewables. In fact, in the G20, it's about almost 120 times increase. Now, it's still a relatively small percentage, but that is a trend that is going to continue. Fossil fuels, which is rather interesting, it's still increasing, but that almost seems contrary to what we understand, because we think that in the US, we've seen many coal plant closures. Europe, Canada, other countries and regions have decreased their coal, but we're still seeing an increase in fossil fuel use if you look at on a global scale. And we'll get into that here in a minute. So let's look at percent electricity by source. This is very regional dependent. If you look at the European Union, of course, they have a rather large percentage of nuclear. Coal has been dropping quite a bit. Some of that is being made up by gas, but it's also being made up by much more extensive use of renewables. Now you go to a country like India, where coal is increasing quite a bit, even though you still see some renewable penetration. Coal is still a dominant energy source. Of course, South Africa, almost exclusively, their energy source is coal, with a little bit of renewables coming in. North America, of course, which all of us would be the most familiar, coal has been decreasing over the years, over the decades, and a majority of that is being made up by increases in gas and also a broader deployment of renewables. And you can see South and Central America and South Korea as well. So understanding how energy is going to be part of the decarbonization transition moving forward is not going to be the same for every region, or even every certainly every country, but even every region of the U.S., which I'll show you in a few minutes. One country I did not have on here is China, but needless to say, very similar to India in a very strong increase in the amount of coal generation. So I think what this information really starts to get across, I hope, is that there really is no single energy supply technology that's going to be the solution. Optionality is really not an option. It's really a requirement. We have to have a broad variety of energy producing technologies. We also want to try and decarbonize those, but we cannot rely on any single option. And this really gets me to what the theme is going to be through the remainder of the talk today. And I'm doing these in terms of 5 what we call practical realities. The first one that I'll touch upon is that we need to use all these tools in our toolbox so that we can still have a reliable and affordable energy transition. We are going to have to, in the future, rely on new energy technologies, but we need to learn by doing. And I'll get into this in a minute, but suffice it to say that as you have new energy technologies in the demonstration phase, if you look at historical development of energy, it takes a decade or two before those technologies really start to become mature. And you need to have multiple demonstrations that have been put in place that are successful so that the industry as a whole can learn from those new technologies that are being deployed. We want to try and accelerate that if we can, but that's a very important step. But that does take time. We also need to be innovative and continue to be innovative in looking at advanced tools and approaches that can really allow some fundamental changes in the supply chain and also in energy itself. Things such as the hydrogen economy. There's quite a bit going on in terms of ammonia power generation. I'll touch on that in a little bit as well. And finally, we need to look beyond just the energy sector in terms of being able to understand what other industrial sectors are utilizing for energy solutions. We need to leverage that as we can and use that where it's possible to achieve our net zero goals. And of course, at the end of the day, I'll summarize in probably the principal practical realities that there's really no one size that fits all. So these practical realities, I'll start diving into them now. These practical realities are really applicable with the backdrop that there is an urgency to keep energy flowing. It has to be affordable, it has to be reliable. And in fact, we're going to see this urgency and demand for electricity increase significantly in the future. Let me start by just setting a baseline here and showing what the capacity in the US is today. Now, it's important to make the distinction between capacity and actual generation. And that really comes to play when you're looking at the renewables technologies. When you're talking about a thermally based technology, such as natural gas combined cycle plants, coal, combustion turbines, nuclear, and even coal plants that may have been converted to natural gas, which would be the gas steam turbine area, those are considered dispatchable technologies that, unless they are down for maintenance or other outages, can essentially produce power 24/7. Non-dispatchable, and so I guess the point is there that the natural gas combined cycle, if there's 325 gigawatts of capacity, if all those plants are operating, they're producing 350 gigawatts or 325 gigawatts of power. When you look at renewables technologies, you have to consider the fuel source. which is an intermittent fuel source. So solar and wind specifically. Batteries somewhat because they also have to be charged generally by the renewables. Those are considered intermittent resources. So even though a large capacity may be available, it stands to reason that if a region of the country has a large amount of wind available, if the wind's not blowing, then you obviously are not producing the energy. So it's just a distinction to keep in mind between capacity and generation. And you'll see where that comes into play a little bit later. But this is our landscape of what's available today. Now, going forward, everyone's been talking about artificial intelligence, right? The race is on. It used to be that the race was on to see who is going to have the AI technology, or can we develop AI technology. I think what we're seeing now is that's really not the relevant point. Now it's going to be, how are we going to power this AI revolution? And that's going to be a significant change. If we look at some of the historic information in terms of data centers, right? Even back in the early 2000s, when social media really started to become more widespread, we saw a slight increase in the demand for electricity. But something that was able to handle with our existing technologies, and it wasn't that critical of a concern, especially when you couple efforts such as energy efficiency initiatives. Over the last maybe 15 years or so, we saw a little bit of an increase again in terms of data center growth due to cloud activities, cloud-based services. The real change is going to be what's happening now with AI. There are several different projections that are available in the industry, anywhere from an anticipated perhaps 3% growth up to about maybe 6% growth in energy demand, just due to data centers. However, what we are hearing and talking to our members, which are generating companies that are specifically contracting with data centers for power supply, is that we could be seeing up to about a 15% increase in demand. That is a tremendous amount of growth in energy that's going to be required just for, or just primarily due to anticipated growth in data centers. Is it going to be that high? Nobody knows, but it does represent a significant increase in what we think we're going to see in terms of demand. Well, so what can we do to meet this demand growth? The point I want to get across is that no single technology is going to address this demand growth. We're going to have to use all the tools we have. In other words, all the energy generation resources we have in our toolbox today to try and meet that demand growth for some period of time, until we can start to see advanced technologies become more widely deployed. So this gets us to our first practical reality. Again, we need to use all the tools in our toolbox, all the energy resources that are available that we have today. We have to use those, keep them as reliable and affordable as we start to use those into the energy transition. So let me focus on just a couple different areas here regarding this practical reality. And I'll start by looking at a little bit of the renewable area. As everyone might expect, renewables has increased significantly over the last 20 years or so. We're anticipating by 2030, we're probably going to have a 2.5 times growth in solar. And you can see the distribution there between global and what we may just see in the US. We're going to see a significant increase in wind. And fortunately, which I think is very much needed, we're going to have an increase in energy storage capability, which is really critical if we're going to allow renewable technologies such as wind and solar to be able to provide that power after sunset, and if the wind is not blowing and producing energy. energy storage is going to be critical. Of course, the key is they're very expensive right now. So that is something that needs to be addressed during the energy transition. If we look at the global growth in renewables specifically, we're seeing that about over 80% of the growth is really accounted for by the European Union, China, and the US. Even though China is also producing a tremendous amount of new coal capacity, they're also one of the leaders in renewables. The economy in China is just growing so dramatically that the energy demand there is increasing quite a bit, and they are going to be producing a lot of new energy resources. And of course, over the years, the share that renewables provides to annual power capacity is also increasing. But it's also not the same, even if we look in the US, it's also not the same in different regions of the US. What I show here is the energy supply by region, and we're using the independent system operators. So that is a controlled region, several regions in the country in which the energy supply is controlled by the system operator. So plants will come online and offline. Maybe energy is imported based on the signaling and the operation from the system operator. I show 5 different regions here in the US. The upper left is MISO, or Midwest, independent system operator. And the upper right is New England. Bottom left is the Southwest of the US, Southwest Power Pool. California is in the bottom center. And ERCOT is a bit of a unique situation. That's basically Texas. And ERCOT has very limited connection to the other systems in the country, whereas most of these system operators can import power or export power across system operator boundaries. ERCOT is essentially an isolated situation. But you can see a wide variety of power generation sources used just within different regions of the US. Nuclear, of course, is all throughout the US, so it tends to be a good solid baseline. But depending on the region of the country, New England tends to rely more heavily on gas. And this is just data from one day over a 24-hour period in one day as an example. But there is some limited solar, but mainly gas and nuclear. In the Midwest, there's still quite a few coal facilities, but you have some renewable penetration. I think California is an interesting situation where as you go in the nighttime hours, or I'm sorry, the early morning hours, you import a lot of energy into California until the sun starts to come up, right? And you can generate a massive amount of energy through the existing solar facilities. Then you start to ramp down all the other power plants, of course, until solar then goes offline, and then it's needing to import energy again. All right, I'm going to spend a couple minutes on this. This takes a little bit of unpacking here. I mentioned before the difference between energy capacity and actual energy production or output. Got a couple things here I want to get across. On the right side of the screen is a look at one day in April, a 24-hour period in April in ERCOT, so in the Texas system. And each of those gray lines represents one day's output for wind. So first of all, you can see a large variation in the amount of wind energy that is produced on any given day, the same day in April. If you look at the averages, a 30-day average, what's the average wind output? It looks relatively steady. However, there are times when you could look at 2 specific days You may have more wind energy early in the morning when perhaps it's not quite needed. During the day, you see a big drop in wind energy, and then it may increase in the evening. Or, just a couple days prior to that, you may see actual decrease throughout the day in terms of wind. Now, on the left side of the screen shows a 5-year period. Again, this is looking at a day in April, but over a 5-year period. Well, it's actually looking at several months over a 5-year period. What you can see is that the installed capacity of wind and solar in ERCOT has increased dramatically, which is expected, right? Because we're seeing that growth in wind and solar. However, it's interesting to look at some of the variations in that wind. If you have the maximum wind for the hour and the maximum solar in the month, you can see that that combination can provide over 30,000 megawatts of energy now in January of 24. You can also see the average hourly wind, and if you have the average hourly solar in the month applying. What's interesting to note, I'm going to use the laser pointer here, is this bottom line. There are times where, due to weather conditions or the time of day, you may experience both the minimum wind generation and the minimum solar generation, which is counterintuitive because we're seeing the capacity of wind and solar increase. So this is a critical point. Even though renewable deployment is increasing and has the potential, on average, to provide significantly more energy, there are times when it's not going to provide that energy, which means there needs to be sufficient backup generation resources to account for that, or you may get into a situation where you have to do load shedding, right? Or you may not be able to otherwise meet the demand. This really came to play, and there's a couple things here I want to talk about. Winter Storm Uri, which happened in February of 21, so 4 years ago now. The ERCOT grid was actually just a few minutes away from complete grid collapse. Fortunately, that didn't happen. But if we start looking at what's happened in ERCOT over the last 10 years, you'll see that the nuclear generation, the installed capacity of nuclears remain the same. Of course, there really was no solar in 2011. By 2020, you had several thousand, maybe 6,000 megawatts of solar. Of course, coal plants have been starting to shut down, so you see a decrease in coal. You see a tremendous amount of increase in wind generation over that time period in terms of capacity. And natural gas has remained relatively stable. So during Winter Storm Uri, and I'm showing data here in the middle of February, so this is still winter months. However, if anybody remembers that storm, extreme cold spell during that time period in ERCOT, which is not something that happens very often, but it still is considered winter time frame. Because of the time in the evening and because of the weather conditions, there's no solar generation and virtually no wind generation. Now, because of that, and because there was some load shedding, actually some of the gas plants had to shut down as well. But you had significant load shedding because of the inability for the existing power supplies, energy resources to meet the demand. Now, this is an extreme, and of course it happened during a time when you might expect weather extremes, very cold temperatures or very hot temperatures. However, This also happens in what we call some of the shoulder time periods. So if you're looking at April, October timeframe, that's when many thermal plants will do their annual, or every couple of years they'll do an outage for maintenance activities, maybe some other repair activities. Generally, because the demand is always considered to be less during those time periods. Not very hot, not very cold. That's why we call them shoulder months. But there have been more instances now where we're starting to see load shedding in these non-peak times. And it's again, partly because of the combination where wind generation and solar generation may not be able to produce its maximum potential output due to weather conditions. And if that's the case, and there is limited backup generation, then the only alternative is to start load shedding. So we're starting to see this happen more often. Certainly, energy storage is one of those newer technologies that we think will have an important role to play to help shore this up. But again, we're having to meet some of these challenges of the industry, such as data center development, with what we have available now. And so these are challenges that are going to be there for a while. So on top of this, we also have environmental regulations. Now, this came out a few years ago, the 111 environmental rule from the EPA. Do not know the status if this is going to be perhaps rolled back, but needless to say, this can have if this rule stays in place, it may have a significant impact on available generation. Basically, this rule requires that carbon capture and storage be implemented in coal facilities and more specifically for gas facilities to reduce carbon emissions. And if we look back in 2023, we had about just under 200 gigawatts of coal capacity available. According to the regulation as it stands now, that would significantly start to decrease in 2030, with all coal essentially being gone by 2034. Now, if you looked at what the plan for the normal retirement of these facilities would be, there's a significant amount of this dispatchable generation capacity that we are going to be missing. So what is going to make that up? Very likely that would be made up by increasing natural gas combustion facilities. And those will also have to have carbon capture and storage installed as well. What's interesting to note is in order to start to get the gas capacity up to, a comparable level that would be a good contributor to the overall energy mix, we would need to add, according to the slope, about 20 gigawatts of gas capacity per year. Now, what's significant in that number is that's the largest capacity installation that we've had in the history of gas plants here in the US, is 20 gigawatts a year. That's the largest we've ever built in 1 year. We would have to do that every single year starting in 2028 for the foreseeable future. So that's a significant expansion of gas that will be required in order to replace that dispatchable capacity. Now, that seems all well and good, but the challenge there is some of the supply chain issues that we are starting to see, not just from a materials perspective or from a workforce perspective, but as an example, I show, I'm not going to get into this in a lot of detail, but just as an example, for the last 4 years, or last 5 years, 2019 through 2023, if we look at the total number of orders for gas turbines from the main gas turbine suppliers, we see that in the Saudi Arabia region and in the Gulf region, we had about 11,000 megawatts. of capacity ordered. Just in the 3-month period in 2024, we've already seen almost that amount being ordered for new facilities in Saudi Arabia. Tremendous energy production expansion underway. What this is signifying is that the supply chain just to order gas turbines is being challenged. Production is not able to ramp up sufficiently. So what this means is, if you start to dive into this deeper, is that a larger number of the existing orders may be taken up by areas outside of the US, which means the remaining available supply is either one going to be longer term lead time to acquire, and it's probably going to be more expensive. So there are supply chain challenges that are going to come into play here as we move forward. All right, so let me kind of wrap this up for this first practical reality. This is the longest one of the group. If we look at the existing technologies we have now in our toolbox, existing coal, the gas fleet, hydro, and so on, and some of the other renewable technologies plus nuclear, they have been in operation for decades, some of them. They're in either already being scaled up or they're in operation. And in fact, many of those are looking into the area of, can we repower, can we retire, can we refurbish these activities or these generation resources? But there's a large number of emerging energy resource technologies, coal plus CCS, being able to put carbon capture and storage on an existing gas facility, advanced nuclear, long duration energy storage. Those are still in various aspects of development. The trick is we have to shrink this white space. As I mentioned before, that's usually a 10 to 20 year period, needing maybe 10 to 12 of these plants to be ready to be deployed so we can get up the learning curve in these technologies. We have to shrink this white space and try and accelerate the deployment of those technologies for decarbonization. So I would recommend, I would state that there's really an urgent need to accelerate some of these dispatchable technologies that are coming in the future, whether it's long duration energy storage, if we're talking hydrogen or advanced nuclear. Certainly the first deployments of these are critical, but we have to move from the first of a kind to maybe 10th of a kind before we can develop that understanding and best practices to make these viable in order to provide safe and reliable energy. So this leads us to our practical reality number 2. We really need to enter the learn by doing stage for some of these emerging technologies. We need to jump in and try and work with collaboratively work with our industry members to try and learn from some of these first movers. And I've got just a couple examples here that I'll show you. I can't talk about all the technologies, but there is a significant amount of new nuclear technologies in the news. I think we've all been familiar with some of the Generation 4 technologies, advanced gas, high temperature reactors that have been under development for decades. Also, small modular reactors seem to be gaining a lot of momentum. But there does seem to be a lot of discussion in the news focusing on new nuclear. And I kind of summarize that here in this chart. You can look at North America, parts of Europe and Asia, South America, where there either are operating reactors or in some places operating reactors under construction. I think what's interesting is to look at all of the countries and regions in green. So these are new countries that are entering the nuclear power club, if you will. Those that are considering it, and those that are at least expressing interest in continuing nuclear. Some of the technologies I think that we're seeing that may come out hopefully in this decade There is a high temperature reactor that's actually under construction in China at this point. There's a variety of different technologies that are being developed. Some of these are considered the Generation 4. Small modular reactors probably one of the front runners, I think. So there is a lot of interest in nuclear. We think it is going to have a role to play moving forward. And I think it's pretty exciting to see what may happen here. Another aspect is looking at energy storage. I mentioned before that it's very important for the industry to effectively deploy reliable and affordable energy storage technologies. That can help address some of the issues in terms of having available backup power for intermittent renewable resources when conditions are such that their production may diminish. There is a significant increase anticipated in the capacity of energy storage in virtually all regions of the world, not just in the US, but everywhere. And in fact, EPRI is tracking over 120 different technologies through our long duration energy storage program at EPRI. There's a database available where we are tracking the development of a variety of different technologies. You can see this is just a scatter plot of all the different company logos, but looking at batteries, novel battery techniques, also looking at thermal energy storage, where you may have concrete blocks that contain tubing where water might be put inside, maintained at a very high temperature and pressure, so that is a heat transfer block, if you will, a storage block in which the energy can be removed. There's quite a bit under development. There's actually several public-private projects that are supporting long-duration energy storage. I show a few of them up here that have all been received Department of Energy awards recently. EPRI is engaged in these, trying to look at different forms of energy storage and show their feasibility. In addition to looking at some of the newer long duration energy storage technologies, I mentioned another aspect is the existing power facilities can look at either retrofitting or perhaps repowering as well. There's some actually very exciting activities going on here. If we look at, this is, I believe this is the Heikkinen power plant in Japan. They are working with IHI and they've already completed a successful demonstration where they replaced several of the coal burners in this plant with burners that would co-fire ammonia with the coal. It turns out that ammonia can be a very feasible drop-in fuel. They are continuing with this demonstration to go up to 50%, and ultimately they are targeting 100% ammonia generation as a fuel in an existing coal facility. The advantage there is you eliminate the CO2 emissions. There's still concern about NOx emissions and other emissions, but we think that can be addressed. But you have a very highly invested asset that now no longer would be considered stranded. It can be refurbished and repowered under newer technologies. And in fact, that's been done quite a bit already. There's quite a few coal facilities in the world that have been repowered with natural gas. This is just taking it, I think, one step further. Of course, CO2 capture and storage is something that we think can be added to these facilities and ultimately leading us to 100% low carbon fuels. Hydrogen, of course, is a big player there as well. So again, it's really time for us to learn by doing. And this is something that we are emphasizing in some of our activities within EPRI, working with our industry colleagues. We want to enhance innovation. We want to maintain cost efficiency in some of these advanced techniques. We also need to address some of the regulatory risks and address some of the regulatory issues that may apply to these. So it really does take a coordinated effort across the industry. Okay, this gets me to practical reality 3. We're in the home stretch here. We need to advance tools and approaches. In other words, we need to enhance innovation so we can make some fundamental changes in the supply chain. Also looking at workforce issues and to support the energy economy as a whole. Just to give you an indication of some of the challenges regarding supply chain, I mentioned a little bit of that before with some of the gas turbine orders that we've seen in the industry. If you look at I'll call them the Magnificent Seven, the big tech companies that we all are aware of, they have over a $13 trillion market cap, okay? The top 100 electric companies only have about a 20% of that market cap. So when we look at supply chain competition, who's going to be the elephant in the room here? It's probably not going to be the electric companies. And we then find that some of our facilities obviously are older. And what that can result in is, we've seen this in the nuclear side for quite some time, obsolescence of spare parts. Being able to find unique valves or pumps or other major components can be a significant challenge as some of these facilities age over time. We need to have a diversity in our supplier base. We need to be able to optimize our assets better in the operation of those assets. We need to be more proactive in how we talk with our suppliers in being able to have long-term stability in replacement parts. Standardizing specifications is something that we always work with our codes and standards groups to try and minimize impacts from that. One aspect I'd like to get into, which is pretty exciting, and there's a lot of support now across the industry for this, is in what we call advanced manufacturing. Powder metallurgy has been around for decades. Additive manufacturing, or 3D printing, if you will, has been around for quite some time. There is a large effort in the industry to now use this type of approach to do large components at full scale. If we do that, we can create some of those unique configurations that may no longer be available. We can reduce the cost, we believe, by being able to produce something that's near net shape to begin with, minimize the amount of welding or machining that may need to be done. And we really think that this can have an impact on both conventional power generation and also some of the new technologies that are coming online. Of course, codes and standards is a significant element of that as well. There are some demonstrations that are underway right now through the companies, through EPRI, and participation with the companies you see on the screen. A couple of the examples, using powder metallurgy and hot isostatic pressing, we can do pressure reactor heads, right, on the nuclear side. So far, the demonstrations that we've done, we can eliminate thousands of hours of machining capability, which means we can get the part produced faster and less expensively than what was done in the past. Right now, if you wanted to, and these times are probably even short now, if you wanted to put an order in for a forging, you can have up to a 5-year wait in available suppliers for that type of component, whereas you might be able to do it in less than a year if you can follow some of these advanced manufacturing techniques. There's others too, electron beam welding, and you see diode laser cladding, which can put cladding on the inside of pressure vessel materials for corrosion protection at significant cost reduction. There are opportunities here, we think. We are working with universities across the country and with various industry partners to try and accelerate some of the development in these areas. There's a lot of I think opportunity here for continued development, and encourage anyone who's interested in materials. This is I think a field that's going to expand quite significantly. Okay, so let me kind of start wrapping this up here. If we look at the energy supply, you know, the slide says it's simple. Well, okay, it's somewhat simple today. We are looking at primary energy sources, most of them thermal, but we have renewables and we have some bioenergy. Most of that is used for electricity generation. Some of it is used for oil and gas for refining activities, or maybe biorefining like biodiesels. Those energy sources primarily through delivery mechanisms go into our industries of today in end use, whether it's buildings, transportation, industry, et cetera. What's this going to look like in the future if these regulations that we see, some of the environmental concerns, new technologies being added, it gets significantly more complex. We will have CO2 reduction, carbon capture and storage applying across almost all of the thermal power generation sources. If we are going to proceed with a hydrogen economy and also perhaps ammonia as a fuel, there's significant energy that's going to be required for powering those aspects of the industry. We might also be looking at things such as direct air capture for additional CO2 sequestration efforts. It's going to be significantly more complex. I think that gets us to our practical reality number 4. We need to leverage solutions beyond just what's in our power sector if we're going to try and achieve some of these net zero goals. Probably won't spend a lot of time on this, but I do want to emphasize that there are a lot of decarbonization options across the industries. And I think we can learn from what's happening in these other industries so that we can benefit each other. For example, carbon capture using cement and concrete to actually capture some of that carbon is something that's already being looked at. Obviously, aviation does a lot in looking at biofuels, but there's also hydrogen derivatives that could be used. Marine shipping is an area where I know IHI and others already have in place ammonia combustion turbines used to power some of the marine shipping capabilities. So there's a opportunity there for expansion as well. And also, of course, I think in some of the short and medium duration energy storage options that will be coming down the line, I think that's going to help again in developing clean electricity as we move forward. My emphasis here is that we really want to have an integrated approach to decarbonization. We are going to have to use all the different technologies that are available. If one is seen to be less effective or less reliable, or from an economic perspective, it's perhaps not as feasible as other technologies, we want to have that flexibility so that we can still maintain a reliable and affordable energy economy, but still maintain resilience. All right, that gets me to the last practical reality, and then I'll have a few closing comments. There really is, and I said this at the beginning, so hopefully I've demonstrated what I said at the outset. There really is no one size that's going to be the solution for what we as a society are trying to do in terms of decarbonization. We must maintain affordability and reliability of the energy system, both now and of the future. But we need to be innovative to try and transition that existing fleet of energy resource options through new technology development into a decarbonized system in the future. There's a lot of pathways that we can do to go down that road. And that's exactly what I want to touch on in my closing comments. The program that I manage at EPRI is called Generation Transitions. And if you visualize the generation fleet of today, our existing generation technologies on the left side, at some point in the future, maybe it's 2050, maybe it's some other time period, our target is a net zero generation fleet that's reliable, that's affordable, that shows resilience for some of these weather conditions that we're seeing that may continue. The problem is, how do you get from the left to the right? So if you use a Google Maps type approach, there's a lot of different paths. Anyone who's tried to drive any long distance knows that an accident happens, you get rerouted. Well, it may take you longer to get there. Same thing holds true as an analogy with technology development. There are risks that the industry will have to take if they're going to try and travel down a specific path and try and rely on a specific set of energy resources. The program that I manage is trying to identify what those risks might be. Once we identify those risks for the various energy technologies, then we can look at what's happening in the industry, either through our member companies or elsewhere in the industry, to understand how can we possibly mitigate those risks. And with the information available to the energy industry, if we can address those risks, minimize those risks, that makes the path from the left to the right just a little bit easier. I think with that, I had a couple more slides, but Ramesh, I think I went a bit over. So let me open it up for questions. I didn't really see anything in between, but I apologize if there were some that I missed, but I'm happy to try and address any questions now.
Oh, terrific. Wonderful talk there, Stan. So as I mentioned in the beginning, I'm going to open the floor for questions. Questions first from the students. So students, if you have a question, please unmute yourself, introduce yourself, and ask Stan the question. And Stan, if you want, you can stop sharing so you can see the full screen.
Okay. What I will also say too is if for whatever reason I'm not able to answer the question, if you could, I don't know if, well, you could send it to Ramesh, but I'm happy to answer any questions outside of the webcast as well.
Yeah, perfect. All right. Questions for Stan?
Yes, I do have a question. My name is Abigail Coyle. I'm a third year here at Lehigh University. And I was wondering, I've heard that there's been issues in the nuclear industry about with not having people interested in being nuclear engineers, not being able to get enough personnel to run the plants. Is that also an issue in any other aging power industries?
Good question, Abigail.
Yeah. Hi, Abigail. Thanks for your question. Yes, as a matter of fact, in the interest of time, a couple slides I was going to present at the end are on workforce issues. One of the things we are doing in the program I manage is we started by developing what we're calling a series of risk registers. And it's basically understanding from our members what risks they see in energy technologies moving forward and being part of the energy transition, whether it's coal or gas with carbon capture, nuclear, even looking at renewables. And I will tell you that every single one of those energy resources, one of the high priority issues they all have is workforce. And it's not just workforce, it really covers a broad spectrum. It's training craft people, so looking at welders, carpenters, boiler makers, millwrights, training those individuals across a variety of energy technologies and keeping them interested in staying in that field. But it's also educational as well. Looking at, that's why I think the engineering, this Lehigh program is so critical, because there are several of these across the country that are looking at getting students such as yourself involved in the energy industry. And I think what I wanted to do in this presentation is to show that there really are a lot of opportunities. There's a lot of cool stuff. That's really about the only way to say it. There's a lot of cool stuff that we're doing, and it's going to become even more critical as we try and go through the energy transition. But training, keeping students, getting students interested, keeping them engaged in the industry. Also, as you might imagine, it's a challenge if you're a worker, an employee with some experience, and you're working at a coal facility in the U.S. somewhere, and you know it's going to, or you've been told by corporate it's going to retire in 10 years, but you want to work another 20. Well, you're not going to wait 10 years until you get laid off. You're going to start looking for a job right now to try and transition. The industry, there's a lot of active engagement by elements of the industry, even including labor unions, even some of the craft groups, our member utilities, educational institutions, to make sure that there's retraining opportunities for those individuals to transition to a different line of work. But we also want to make sure that if a plant is going to operate for another 10 years before it shuts down, you need qualified people at those plants to make sure that it continues to operate for that length of time. And who knows, what we're seeing now is some of the coal plant shutdowns may get reversed. So you never know what's going to happen. But I think this is a very widespread issue. It is a concern that I think we all share. But we actually had a workshop through the program I manage in early February, where we brought in participants from labor unions, craft groups, equipment manufacturers, engineering, procurement, and construction contractors, to understand the different perspectives of how they all see this workforce issue. And there's a lot of commonality. And I think there's a lot underway now, but it is going to be an issue moving forward. So, great question. Thank you for that.
Questions for Stan from students. Please unmute yourself, introduce yourself, ask the question, please. Students.
Hi, my name is Sajjad Al-Shamari. I'm a student in ESE. I have a question. We see it right now, the weather changing. It's a lot of hurricane and a lot of heat wave and summer. This will be increasing the storage system for keep more power available, or increasing the micro nuclear. Thank you.
Yeah, I think we are going to see, well, we've already seen severe weather situations, severe weather events. Part of the challenge, I think, in terms of the energy system has been, and again, like I said before, we need all of the different energy technologies, but historically, the energy system, if you will, in any region of the country would always maintain what's called a reserve. So a capacity, the demand may be 100 gigawatts in a region, but there's actually available generation of maybe 125 gigawatts, just to account for plants being shut down for outages, severe weather situations where the demand is higher than you anticipated. What we've seen is those energy reserves have slowly been shrinking. A variety of reasons for that. But that is an increasing challenge for the energy system, because now some of these extreme weather events, if the capacity is no longer there to provide that generation, that's when you start to see more load shedding. I think, personally, I would like to see more nuclear. I think that is a very relevant zero carbon base loaded dispatchable generation that can provide a lot of energy. But certainly renewables has a role to play. I think as we get into more energy storage deployed, I think that can become a bigger factor as well. But I think we are going to see probably, weather events having increasing impacts. Data centers, if we start to see a significant increase in demand due to data centers, I think that's going to be a very significant challenge. Matter of fact, my understanding is that data centers are already now reaching out to specific utility companies for a dedicated power plant just for that data center, which would be what we call behind the meter. So that power plant would not be putting energy on the grid, but just supplying energy to the data center. But of course, that power plant no longer can provide energy to the grid. So how does that impact reliability? It's a lot of challenges moving forward.
Thank you.
Yeah, good question. So, question for Stan from students. I see something on the chat box. Tommy Parisi, if you want to ask that question yourself, or you want me to read this out? Okay. Along the lines of optionality and working outside the box of the power sector, what are the best options for mitigating load growth, especially considering the continued rise and prominence of data centers?
So I think I think it's really hard to say the best option for mitigating load growth. As I showed in some of the slides, it's really going to depend on regions of the country. The energy supply mix is different, even within the U.S. when you look at different regions of the U.S. And of course, globally, you see quite a difference in the energy supply mix. In terms of mitigating load growth, there's certainly, and this has been underway for decades, a tremendous amount of energy efficiency work has been done. I mean, just think of, very simple, going from incandescent lights to compact fluorescent, now to LEDs. All of that didn't just happen. That was actually a concerted effort by a lot of the industry in terms of improving energy efficiency of end user devices, so that we can try and mitigate some of that load growth to prevent some of this load shedding that we are now starting to see. I think, data centers, again, is going to be a challenge. I think the uncertainty there is we don't really know what that load growth is going to be. There's various projections, but as you should know, any projection is wrong. any modeling is based on the input, right? So assumptions change over time. But I think we have to keep all options open. But there's more that comes into it. It's also energy efficiency. It's maybe shifting to time of day messages as well in terms of energy usage.
I see yet another question in the chat box. Kirby Sleer. Question number one: how open do you see the various stakeholders in accepting the idea of learn by doing? I see this diverging from the historical norm of making sure technology is vetted to make sure or reduce the potential for failure or less than planned outcome. That's a good question.
So I will say that I think that's, again, another aspect that's unique for EPRI. We've been doing this since EPRI's history, to be honest. For example, some of the earliest carbon capture and storage technologies that have come out of the laboratory that are now in demonstration phases, we can easily go to a handful of our energy provider members, right, and say, we've got this new technology. We would like to install it in your plant and see if it works. You can't do that very easily on the nuclear side because of a lot of the nuclear restrictions. But on the fossil side, we've demonstrated countless technologies. Maybe we pull a slipstream of flue gas from a coal facility, and we can run it through a new carbon capture technology just to demonstrate its effectiveness. We actually do that quite a bit. So it's very feasible. I think these long duration energy storage demonstrations that are underway, we've already got some of our members that are saying, if this is ready to go, I want to put it in and see if we can use it. So that aspect, I think, is actually good. We have that capability with our members because of the relationship that EPRI has and the way we approach collaboration.
Good. Question again in the chat box. On nuclear, what technology exists to provide the long-term storage of spent fuel, or what form of recycling?
Boy, okay. Well, we had that. It was called Yucca Mountain. Unfortunately, that did not get the regulatory hurdles became too great. I've been out of the nuclear field for a while, but Ramesh, you might be able to help. My understanding is that France still reprocesses its nuclear fuel. Is that correct? Do you know that?
It is correct, and so does another prominent utility in the U.S.
Okay. So it can be done. The technology is actually there to reprocess spent nuclear fuel and reuse it. There's also, I believe there are in Europe storage facilities for spent nuclear waste underground that can be monitored, and it's a retrievable site. The politics in the U.S. and the regulatory requirements have made that a challenge. But I think the technology is there. I think one of the attractive aspects of the small modular reactor is it negates the need for periodic refueling. So, after so many years, it can be pulled out, another unit put in place. But of course, the waste is still something that has to be done. I think from a technology perspective, that's not the hurdle at this point.
Yeah. And of course, there's this reactor design that Bill Gates is backing, which is will be using spent fuel. So that's another kind of something to look forward to. Questions for Stan, the general audience.
Hi, my name is Spencer. I'm an undergraduate studying economics. Is there a certain method that you think we should take to decide what path to decarbonation we should take? Like, should it be up to policymakers, or like, do you think like we should take a more free market approach to deciding that path?
No, that's a very good question. That's I'd be guessing if I tried to answer that. I guess I will say that based on our experience working with the industry and specifically our members in our research area, there's really not going to be one approach. We do a significant amount of modeling within EPRI, looking at future scenarios and how the economics of that might play out. And of course, as I said before, all of those are based on assumptions. So if the assumptions change, you gotta look at different scenarios. But I think over the decades that we've actually been doing this, I think there's been one consistent base, and that is that, and again, I mentioned this during the presentation, you have to have all options available. If you have all the options available from an overall economic perspective, it gives you the best chance of being able to address, the identified need, but doing it in a more affordable fashion. If you want to get into specifics of economic modeling, I can hook you up with people at EPRI easily enough. But I think I'll probably leave it at that for now.
Thank you.
But good question. Yeah, thank you.
Question for Stan? We still got a few minutes.
I would also say if there's any really challenging questions, tune in next week when Mike Caravaggio talks and tell him that I said he should answer that question. I report to Mike, so I think you'll really enjoy his talk next week.
Oh, that's a great promotion. Thanks a lot, Stan. So one thing that, if I may ask this question, and I know EPRI does not get involved in policy, but with all these pressures now, to look at how do we treat, our very important source of energy, electricity. And, when you pointed out in the slide that, the Magnificent Seven are 4 times bigger than all 100 utilities. Are there some policies that can be at least considered? I know that an EPRI may be in the best position from their research, to allow many of these technologies to go forward.
Yeah, that's a very good point, Ramesh. I'm glad you brought that up because I do want to point out that one of the aspects of EPRI is that we will never promote a specific vendor or technology over another, because one, we as a nonprofit, we do not show favoritism, right, to any technology or any specific provider, but we also want to retain our independence. And so what we like to do is, based on the research that we perform and the collaborations we have within the industries, we want to inform the policymakers. So we do briefings in the Capitol to the government. We will brief regulatory agencies. We will certainly take our information to codes and standards bodies. But we do that from the perspective of, here's the research we've conducted, here's what we've looked at, and here's where we see this having a role to play. So we want to inform the policymakers in their decision-making process. So we do not set policy, but we will certainly work with all elements of the industry to demonstrate new approaches. Some of those work out great, some of them don't work out. But if we do pursue a technology development that from whatever technical reason does not seem to be feasible, we still publish that, because that's still contributing to the learning of the industry as a whole. I've had a couple different, as an aside, a couple different sensor technologies that I've looked at in the past, high temperature sensors, and a couple of them turned out to not be feasible for that specific technology. But you still want to get that information out there, because again, it helps grow the overall base of information. But yeah, in terms of policy, we certainly do not provide policy or recommend policy, but we'd like to inform the policy based on our research.
I think we have time for one question. Anybody? Question for Stan? Just an excellent presentation, Stan.
My pleasure. And like I said, if there's any additional questions, send them to Ramesh and he can pass them on. I'd be happy to answer, and I can probably provide links to reports on EPRI.com that are available to the public. And I would actually recommend going to EPRI.com, and you can peruse what's on the website there and find a good deal of information.
Oh, terrific. Well, thanks a lot again, Stan. Wonderful presentation. And as Stan pointed out, we'll have next week a talk about the global status of energy transition. And Michael Caravaggio, if you follow his postings on LinkedIn, he just presents these graphs from all over the world that give a very vivid picture of how we're doing this energy transition. I find it very, very useful. In fact, I share it with many of my students whenever I see a posting. So Michael will talk next week. And again, look forward to seeing most of you, if not all of you, next week. And thank you again, Stan.
My pleasure. Thank you, everybody.
Thank you all.
Take care.
Bye-bye.
Thank you.
Thank you.